This is problem 718E. It's on page 393. A wood platform is to be made of standard plywood and finished lumber using the cross-section shown in the figure below. Would the platform be safe if 4 men weighing 250 pounds each were to stand 2 feet apart as shown in the figure part B? Consider only bending stresses. Now, why does he say that? Well, some of you have come up to me and asked questions, and let me just make some quick notes here. You have something simple, like a beam that's simply supported in a load in the center, like there's 2 or 3 problems on your homework like that. You guys know that you can make a shear and a moment diagram. Okay. Now, so far, all we've done is we've considered stresses based on the moment in the beam, right? What about the shear? Because there's also shear in the beam too to consider. Well, because shear doesn't usually get big enough to cause failure in the beam, we haven't considered this yet. We will in the next chapter. So far, what we're doing is we're considering the moment, of course, the maximum moment, and what it would do to the beam. Okay, so we're getting the stress, ideally at the maximum moment, and of course at the maximum cross-section position. Okay, does that make sense? So anyway, we'll do more with this later. We're going to go on and consider what happens when you have shear. And you can actually put the two together, but we'll get to that later. So right now in chapter 7, we're dealing with just the moment part and the resulting normal stress. Okay? So in our particular problem, we've got 4 loads, and what I did first, bless you, what I did first is I came up with the shear and moment diagrams. You guys can see this pretty easily. I'm not going to go through all the details. There are reactions at either end. Each man is standing 3 foot from the end and then 2 feet apart, and each man weighs 250 pounds. Now you guys without statics hopefully can tell me the reaction loads, right? How much are the reactions? 500 apiece, good. All right, they'd have to be the same because this is a symmetrical thing and have to sum up to the total load, so that makes sense. What about the shear diagram? So far, the questions I've had have all been about shear and moment diagrams. What would the shear diagram look like? Well, it'd be 500 pounds. And then it would come down by 250. So this section's at a shear of 250 pounds. Would go down again by 250 and be at 0. So the shear in the beam in this middle section is actually 0 up until, keep everything aligned, up until we get to the next load where it comes down to a negative 250 and another negative 250, so negative 500 in total, and back up to 500 at the end, or back up to 0. Away from 500 at the end. Okay, so that would be the shear diagram, but again, we're not dealing with the shear in the beam and asking what kind of stresses does the shear cause. We're talking about moments. Okay, so the moment in foot-pounds force, what would that look like? Well, you just add up area, right? You guys can calculate this area. It's 3 feet times 500. So at this point, we have a moment of 1,500 foot-pounds. Okay. Get a little more area here. What is that? Well, it's 250 times 2. That's 500. So come up at a lower slope, right? Because remember, the shear is the slope on the moment diagram. Since it's lower, then the slope's lower. So add another 500 foot-pounds of moment, we'd be at 2,000 foot-pounds. And since there's no area beneath this section of the curve, what would happen to the moment diagram? Level, straight line, right? 0 slope. That's what this says. So it would stay at 2,000 foot-pounds, and then of course it would just go down to 1,500 and then back down to 0. Okay. Now the section that I'm interested in is the section in the middle. Really this whole section here is interesting because it all has the same moment. So I'd like to essentially analyze the stress where the moment is the maximum, and of course this distance C is the maximum distance from the centroid. Okay. By the way, we need area properties. I went and did that. I did that in the spreadsheet. It's pretty simple. We just got two 2x4s and a couple of pieces of plywood. By the way, I wouldn't stand on this thing. Any offset is going to make the thing probably flip over or crack on one side. But anyway, if we could apply these loads, you know, by picking the people up by crane and setting them down very carefully, I think it might be okay. But anyway, so here's the various cross-section properties. I started at the bottom with the bottom piece of plywood, which is a 1/2 inch tall and 12 inches wide. And so you can see the location of the center of that is just a rectangle, so it's just up by 1/4 of an inch since it's a 1/2 inch thick. And similarly with the sides, basically the next two lines represent the 2x4s on either end. And so I just calculated the cross-section properties of all those. And you can see that the center of the 2x4s is going to be 2 1/4 inches up from the bottom, because you got a 1/2 inch of plywood plus a 1/2 of 3 1/2 inches. Okay. So that's, and by the way, I don't like doing those things in my head and possibly making a mistake. And so you'll notice that in the spreadsheet, I actually just typed it in exactly like I told you. I typed it in as a 1/2 inch plus 3 1/2 inches over 2, just to make sure I didn't make some dumb error. Okay. So anyway, there's the two sides. It doesn't matter which one's left and which one's right. And then finally, here is the plywood at the top. Notice to measure its center point, you'd have to again go from the bottom. So it's 4 1/4 inches from the bottom. So there's the various pieces of the spreadsheet. Over here, for the area moment of inertia of each of the individual components, I went ahead and typed in the equation, just 1/12 BH cubed. And so for the plywood, the height of the plywood is a 1/2 inch, so that's the part that gets cubed. And I was wrong, it's not 12 inches wide, I'm sorry, it's 24 inches wide. So the base dimension of that rectangle is 24 inches. And then so BH cubed over 12. Did the same thing for each of the 2x4s, and you see they come up here. I'll show you one of them. Both the same thing. So the base, the width, in other words, of the 2x4 is 1 1/2 inches, so there's 1 1/2 inches there. The height of it is 3 1/2 inches. You have to cube divided by 12. There's 1/12 BH cubed. So anyway, there's our area moments of inertia. And then this just notes that basically the plywood is the only thing that's really offset. The centroid is offset from the centroid of the combined figure or cross section. And so then the spreadsheet calculates the rest of it. So we've got the centroid height. It's not really surprised that that's 2 1/4 inches, because the overall height of this thing is 1 inch plus 3 1/2 inches, 4 1/2 inches. 1/2 of 4 1/2 is 2 1/4. So that you could have seen by inspection. But here's the one that's a little more difficult to calculate. The area moment of inertia is 107.22 or so. By the way, 107.22 what? Inches to the fourth, good. Okay. If all this other stuff is in inches or inches squared, then I should be in inches to the fourth power. Okay. All right, so the maximum moment is 2,000 foot-pounds. We can plug that in. And since this is a symmetrical cross-section above and below the centroid, then it wouldn't matter if we look at the top or the bottom. It would be the same. So what would be the distance to the outer fiber? Let me draw the cross-section over here. So there's the top piece of plywood. There's a 2x4 and another piece of plywood at the bottom. What would be the height from the bottom, I'm sorry, from the centroid, excuse me. The centroid's just here in the middle. What would be the distance from the centroid to either one of the outer fibers? Half the height, right? 2 1/4 inch. So this would be 2 1/4 inches. The area moment of inertia we got from the spreadsheet, that's 107.2188 inches to the fourth power. Okay, if I remember right. Yeah, that's right. Well, we've got a small problem here. I see feet, inches, and inches to the fourth. What should I do? Well, what do we expect to get out? We want to get stress. What would the units of stress be? Force per area, right? Just like pressure. So PSI would be ideal, right? So I want to get rid of the feet. What I did is I just multiplied 1 foot by 12 inches in the denominator. That gets rid of feet. Okay, do you guys see that these 2 inches become inches squared in the numerator? This is the denominator of the denominator, and so this inches would move up to the numerator. You'd have inches squared over inches to the fourth, and that means we'd just be left with inches squared in the denominator. So it's PSI like we want it. Okay. Anyway, plugging all that in my calculator, I got about 503.64 PSI, maybe exact, I don't remember. All right, so will this thing be safe? Well, that's the stress in the wood, but they didn't tell us what kind of wood this is. Let's go back to material properties, in the back of the book, and look for wood. Page 719, page where I ended up. I couldn't find any wood that was weaker than that in bending, so I said, well, it should be safe then. The weakest wood I saw was hemlock, number 3, and its bending strength was 625 psi. So in theory, this should work. I'll tell you in experience, it's not a good idea. I bought a huge radial arm saw. It's an industrial job, and it's got a 3-phase motor on 220. Well, technically I guess 208, 3-phase motor. Turns out you can actually run a 3-phase motor off of 220 from your home. Yes, sir.
Did you have to multiply it by 2 because it's static load?
You're right. I should have considered that. I forgot about that part. This is a static load, and so your author does have that recommendation. Let's fix this. You're right. So I need to change my analysis. Now, notice they've got page 368, it says the yield strength. And so if they're talking about, so I guess it would depend on how they gave us these properties. If you look at the properties of wood, they're talking about the allowable stress in bending. They're not talking about a yield stress. So I'm not clear on whether they mean that the amount of bending stress it could take is actually 625, or if we should go back to page 368 and say, well, let's take that and consider that that's a yielding strength and then divide it by 2. I'm not clear on which one they're saying. It would depend on how they're defining those properties. By the way, you can actually go, there's a really nice guideline online. Let's see if we can find it quickly. Forest Service wood properties, I think, even. May not even be just engineering properties. Wood handbook, maybe that's it. Wood as an engineering material, that's what I'm looking for. This is a really handy document. I've used it many times before. It's a federal government document, as I recall, essentially. But it gives you properties, not just strength properties, but also some energy properties. Things like if you burn the wood, how much energy do you expect to get out of it? And it's pretty handy. That'll load here in just a minute. Here we go. Yeah, wood is an Forest Service Laboratory. Okay, so anyway, if you look in this, let's do Control F for find. We're going to find a lot of strength information. But anyway, I mean, they've got all sorts of species and things in here. Let's see. Here we go. Control plus. We just went to a random page. Looks like if you're watching the video, we're on, well, it's taking a while to respond. see, they're not telling me the PDF page, but if you look for 5-12, that's the page number if you were to print it. Here's a common species name and a bunch of different information. Normal moisture content, specific gravity, modulus of rupture, elasticity, work to maximum, load, impact, but just all sorts of different types of loading strengths. That's what they've got here. So here's shear parallel to grain, tension perpendicular to grain. That would be what we're, let's see, let me think. Parallel to grain would not be very strong. Tension perpendicular to the grain. This should be fairly strong. Should be, why does that look stronger? I'm not sure. I've wrapped my head around this before. Can't think right now exactly what all these things mean. But anyway, yeah, they have definitions in it too, so you can look at pictures and see what direction they're talking about, which is helpful. This one, the way they describe it, it seems like the one that I would be interested in, but that looks like the lowest strength, and that doesn't make sense to me. Wood has its maximum strength. If you were to try and bend it, well, let's see, the bending moment would be, well, here, let's just draw it. We're going to end up with way too much on this example problem video. If the grain's running this way and you load it this way, then that's the strongest orientation for the wood as far as versus the grain goes. So you don't want to make a beam out of wood like this where the grain is running this way and then load it like that. It'll be very weak. Because basically what you're doing is you're applying let's see, in this case you have tension in the bottom, and it's like you're taking the grain and just trying to pull it apart, which is pretty easy to do, right? Whereas in a beam like this, you have tension in the outer fibers of the grain, and it's going to be very strong in this direction. Okay? So anyway, it's really good information in this. I've used this document many times. I'll try to post a link to it so you guys have it. There's something else I wanted to say. Oh, you were talking about should we divide by 2 or not? I don't know, because I don't know how they gave us their results. If that's the case, then I guess the answer is maybe, right? I don't know if it's safe or not, because you didn't tell me what wood it is in the problem statement. So in that case, we wouldn't know. I'm not sure what plywood's made out of most of the time. Anybody know? Cedar? I'm not sure.
It can be a lot of things.
Yeah, I'm sure it could, especially if you get chipboard. God only knows what it's made out of. So, you know, if we have to multiply this by 2, essentially, then we're up about 1,000 psi, and then looks like if it's any of the number 3s, then it wouldn't work, but any of the other stuff would work. Okay, good point. There's another point I wanted to bring up, and this is worth having on the video too. What if you got a knot in the wood? Well, then the strength's totally different, right? Because then the strength's going to be much lower. And it would depend on the direction of the knot. If the knot runs through the wood this way, look at it like a circular cross-section there, that would be much worse than if you had a knot in the center, right? Of course, a knot on the outside edge would be bad too. Why? Why would a knot the same size in the center not be bad, whereas a knot out near the outer fibers would be bad? It's in tension here. Along the neutral axis, there's no stress, right? So we don't really care what the wood looks like in the center. It could be balsa wood for all we care, right? It would be fine. There's no stress there, okay? What matters is out near the outer fibers. That's where we need the material to be in good shape. So that's one of the reasons plywood is so strong. Plywood helps distribute the imperfections of the wood, right? So that if you've got a layer of plywood that has a knot out of it, if there's now a plywood piece, well, there's another layer next to it that can help absorb the load. So anyway. Also, the other thing that's nice about plywood is they'll orient the grain of the layers perpendicular to each other. So you end up with strength in both directions, which is nice. Anything else? All right.